Hello scholars, welcome. Mr. Hinkle here, and in this discussion, let's talk about the beginning of everything. Where did it all start from? What is it all anyways? It all is the universe, and the universe started 13.8 billion years ago. Crack! Emitting a sound and projecting everything outward from a single location in what we like to call the Big Bang. The Big Bang theory is our current understanding for the origin of the universe. This is what we're getting into, the fundamental principles of the Big Bang. This is our objective for today. So, as mentioned, the Big Bang explains the origin of the universe. It also talks about the evolution and the fate of where the universe might end up, things we're getting into. So, the idea is the universe began as a singularity. Everything that exists in the universe was in a small, supermassive, super hot, super dense single point, a singularity. And then the universe began to expand quite rapidly. And in that expansion, we had structure and order develop. Different forces were applied, stars formed, galaxies were created into what we see today. Everything started from the singularity, and these two lines here are representing the expansion in every direction, formations of stars and galaxies. It's more complex than this, but for our introductory lecture on the Big Bang, I think this is good enough for us. So, how do we know this? Well, there are three lines of evidence. Edwin Hubble, you may have heard of the Hubble telescope, named after Edwin Hubble. Well, Hubble was looking through telescopes and noticed that he would take measurements on this star and measurements on this star, and then do it again later, and those stars were further apart from each other. Kind of like raisin bread when it's rising. The distance between top raisin and middle raisin at one point before it rises is 2 centimeters, and the distance between top raisin and middle raisin later is 4 centimeters. Also, middle raisin and right raisin, 6 to 12. Well, that is showing that these raisins are moving far apart. And so Hubble was able to use the wavelengths of light. It's called the red light shift, the Doppler effect, a little outside of our scope. But Hubble's law shows that the universe is expanding in all directions. And in fact, it's still expanding at an accelerated rate. 2, the cosmic background, the cosmic microwave background radiation, the CMB. This is a signature that is left. This is representing the entire universe, and there is a signature that is left that can be detected, that is the remnant heat from this initial expansion of the singularity, the Big Bang. This is recorded through telescopes. This is how we know all these things. And then the third line of evidence that explains this is the abundance of light elements. And the physics here, the calculus is very complex, but the proportions of the elements, hydrogen, helium, and lithium today, align with the theory for Big Bang nucleosynthesis when the original elements were beginning right here at the very beginning. So, light elements. When you look at cosmic microwave background radiation, and you reverse the rate of expansion using Hubble's law, along with light element nucleosynthesis, and you reverse it backwards, this is how we get this number, 13.8 billion years. The universe is 13.8 billion years according to the Big Bang Theory, which is a calculation based on the expansion of the universe. So the universe, which is made of 5% visible matter, 27% dark matter, 68% dark energy, visible matter being what we can see and record, and dark matter and dark energy being forces that we can observe their effects but not measure directly. It's a really wild concept, way above my pay grade, that's for sure. But cool stuff nonetheless. I like to think about everything that exists in the universe and what we can see and measure being 5% of it. That's amazing. The rest of it? Outside of, well, I'm not even going to go there. Okay, I'm going to keep going. So we've got an accelerating universe because we can observe a mysterious force driving the acceleration. It's called dark energy. It's the hypothetical form of energy inherent to empty space, also known as vacuum energy. It's there we can observe its effects, like the raisins in the bread are moving further apart. In that example, the dough is pushing them apart, but in the actual universe, it's dark energy that's pushing them apart, and it's moving faster. So the universe is accelerating. Let's see. This is our evidence. Here is our age. Here is our model. And then another keyword, expansion is accelerating. Cool. Okay, so the Big Bang is telling us a lot of things. It's also telling us, how's it all going to end? Uh-oh. Should we go say goodbye to our loved ones? Well, let's not jump to any conclusions. We're probably a long, long ways away from this happening. But it's a fun idea to think about. How does the universe, if the universe was born, how does the universe die? Because it is a very macroscopic living organism, kind of like our Earth is a bigger organism than the individual species. That's the Gaia hypothesis. So how does it end? Well, there are three possibilities here. I guess 3 is our magic number for today. The big freeze, the big rip, or the big crunch. So the big freeze says the universe is going to expand until the temperature of the universe is equal in every single area, which will end up freezing the whole universe. The heat death. There's no more heat. It's expanded so big that no more heat is being developed. All the stars are out. We're frozen forever. The big rip. The universe expands until it's so big that it literally rips space apart. I don't quite understand how that could happen, but this is one of the prevailing ideas. The expansion causes the end of the known universe. And then the big crunch is that the expansion gets so great that there's no more energy that can continue to expand it, so it implodes in on itself. Basically, we have the Big Bang in reverse. So what's going to happen? I don't know. Maybe we'll just have to wait and find out. Scientists are studying dark matter and dark energy. We're making observations out into space using the James Webb Space Telescope that we see an artist's rendition of it here. This is the highest power telescope that is collecting images of deep space, rewriting what we think we know about how the universe works. It's a big, big topic. We're still looking for a unified theory for general relativity and quantum mechanics. So 2 of our main ideas in physics, relativity and quantum mechanics. How do we unite those 2? So there's a lot of room to understand what's going on in this great big world of ours. Universe, it's been around for 13.8 billion years. It started with the Big Bang, a singularity, and has been expanding in every direction ever since. We don't know where we are going to end up, but it's fun to think about. It's fun to think about the life cycle of our universe in a similar way that we might think about the life cycle of our own body. The Big Bang Theory, the beginning, the evolution, and the fate of our universe. Thank you so much, and I'll see you again.